So we were talking about multiplicities, and in general, if C is a 0 of P, so C is the value, that's an x-intercept of the polynomial P, the corresponding factor would be x minus C. So to write a factor, you're just subtracting the 0 or subtracting the root. And this occurs exactly m times, so the number of times, that multiplicity of times. Then we say it has a multiplicity of m. So just like what we were talking about, in this one, we set each one equal to 0, x plus 3, and x minus 6. So x equals 0 has nothing to do to it. I can't solve for x any further. X equals negative 3 from this first one, or sorry, the second one, but it's a multiplicity of 2 because of the squared. And then x equals 6 has a multiplicity of 3. So if I write out these zeros, 0 had a multiplicity of 1, negative 3 had a multiplicity of 2, and 6 has a multiplicity of 3. The multiplicity of each 0 will determine how the polynomial will behave when it gets to the x-axis. So if it has a multiplicity of 1, just like this x did, it had a multiplicity of 1. What that's going to do to the graph is go straight through the x-axis. So it goes straight through the x-axis. And we can say it goes straight through the x-axis at that 0. So for this one, it goes straight through 3. This one goes straight through 2, but it's just going through that 0. When m is odd, the multiplicity is odd, but bigger than 1. So if you had something like a multiplicity of 3, multiplicity of 5, 7, and so on, we're going to see it bend or wiggle through that axis. So we could say it bends. Oftentimes I say it wiggles through the 0. So this might be a multiplicity of 3. Same situation here. It's going through that 0, but it bends, so it could be a multiplicity of 3. The difference between each of these is just how close it's getting to the axis. So if it had a multiplicity of 5, it would be even flatter of a wiggle. Multiplicity of 7 is a even flatter, so it just makes it look a little bit weirder, but we're really only going to focus on multiplicities of 3. If it's an even multiplicity, like multiplicity of 2, multiplicity of 4, 6, and so on, it bounces off the x-axis. So it bounces off the x-axis at that 0. Here it bounces off C and goes back up. This one was going up, it bounces and goes back down. So it's not going to go through the axis, it just hits it and goes back the way it was coming from. Before we get to more graphs, let's start out with, can we write the equation of the polynomial given the specific zeros? So if I've been given a 0 of negative 6, we want to turn this into factored form. Now we talked about how the corresponding factor is x minus c. So you're subtracting the 0. What I like to do is say if it's equal to negative 6, there's one of the zeros. And what we did earlier was take each factor and set it equal to 0, and then we solved. So if I work backwards, I'm getting that back equal to 0. So I would add 6 over here to the left, and now it's back equal to 0. So the factor that's associated with it is going to be x plus 6. We have another one at negative 1, so I'd add 1 to the other side. and it's back to 0. Then we have a third one at x equals 5. If I subtract 5 to the other side, it's equal to 0. So we have 3 zeros that we started out with and now made 3 factors. We could say our polynomial looks something like this. A times x plus 6 times x plus 1 times x minus 5. Now I'm putting an A here because we don't really know what the leading term is going to be. We know that these are the associated zeros, but that leading coefficient did not create a different 0. Remember back to in the previous page, we had a -3 here. That didn't create another 0 on top of it. We had a 1/5. That didn't create another 0. That was just a vertical stretch or a vertical shrink. And a vertical stretch or vertical shrink will not affect the zeros of a function. So there's actually an infinite number of possible examples for a polynomial that has these zeros, because I could stretch it by 2, 3, 4. I could reflect it. I could shrink it. All of these things could be happening and still produce these zeros. So I'm just going to wait and we'll talk more about how do we find that value when we get to the graphs. So here, same situation. I have 1 at 0. Well, there's nothing to do for that one because it's already solved for 0. If I had a 0 of x equals -2, we'd add to the other side, and now it's back equal to 0. So there's the factor associated with it. X equals 7, I'd have to subtract 7 to the other side. So x minus 7 equals 0. And then x equals 10. Subtract your 10, and it's back to 0. So in total, we had 4 zeros, which means I should have 4 factors. And I'm going to write this out. Y equals a times, and now one of the factors is just x. Another's x plus 2, so parentheses x plus 2, parentheses x minus 7, and parentheses x minus 10. All of those are the factors. A is just that vertical stretch or shrink. Notice that when you have just an x, that's where that 0 is coming into play. So we'd have an x-intercept of 0, 0 because of this one x. All right, the last one here. We've had a lot of these, but let's say x equals 3/4. X equals -2/5. X equals 8. X equals -3. And x equals 0. For these two, they're special because those have multiplicities, but we'll apply that to our factor here in a minute. So let's work backwards with this x equals 3/4. If I work backwards, I could subtract 3/4, but we really don't want fractions is the problem. So I'm going to undo this because the last thing that would have happened was this division of 4. So I'm going to multiply by 4, and I get 4x. Subtract 3, and now it's back to 0. The factor that was associated with this was 4x minus 3. If we think back to how we had fractions earlier, so we got a fraction of 3/5 in that second example. It came from doing 5x minus 3 equals 0. We added the 3 and then divided by the 5. So since dividing by the 5 was the last step, we multiplied in the first step when we're going backwards. So I'm going to do this again here. X equals -2/5. I already wrote it. So I would undo this dividing by 5. I'd undo it by multiplying. That becomes a 5x, and now equal to -2. We want to move the -2 over, so I'd add it to the other side, and I get 5x plus 2 equals 0. X equals 8 is just easier because we've been doing that when I subtract 8, so x minus 8 equals 0. There's nothing else there. If I add 3 to the other side, I get x plus 3 equals 0. But we need to remember this has a multiplicity of 2. So keep that in mind when we're writing out this in factored form. X equals 0 has nothing here I need to do to it, but it does have a multiplicity of 3. So I'm going to take each of these factors and write it out in factored form. Remember, we have a value here that could be a vertical stretch or shrink. And it doesn't matter exactly what factor we start with, but I'm going to show you why you'll probably never see it written this way exactly. So when I got to the x plus 3, I put a squared on it because it is multiplicity of 2. And then the x equals 0 is just an x, but it has a multiplicity of 3, so it's just going to be x cubed. You'll hardly ever see it written this way because your x cubed term doesn't have another value with it, so it's not like x minus something or x plus something. So usually that goes in the front of the function. So I'm just going to rewrite this as a times x cubed, and then I can write all the other things. So 4x minus 3, 5x plus 2, x minus 8, and lastly x plus 3 squared. You do want to make sure you're looking at what the squared or the cubed with the multiplicities will be. Now the problem with these 3 examples that we have is that we didn't really have enough information to find out what the a value would be. So we would need to be given some type of specific point or some other information to determine what that would be. All right, so that's what we get when we start looking at the graphs.